The humanity, the humans, it's like passengers or crews on a ship already left home, but we don't know where we are going. The ship is already start leaking gradually, and that ship is become crowded. Many people is getting sick. People know that's going sooner or later the storm is going to come, but there's an uncertainty. We don't know when the storm is going to come. If the storm is come, there's a possibility the ship is going to sink, and this is the we are facing right now. Yes, I'm Jonathan Jiang. I started to work at the Jet Propulsion Lab, California Institute of Technology since 1999. So I'm already worked here for more than 22 years there. Part of the reason I do this kind of research, the observations to find directions for us, how to save us, how to move forward. So many of my research papers, the motivation, my wife also asked me, what is the motivation after you doing this? My motivation actually to inspire the next generation of scientists, to inspire the people, the humanity on the world to think about this, how we can move forward and survive.
Yes, I'm Philip Rosen. I'm retired from the energy industry, refining petrochemicals for nearly 30 years, very good 30 years. But I've always had an interest in astronomy, astrophysics, space exploration. As a 4-year-old, I remember watching Neil Armstrong and Buzz Aldrin land on the moon in 1969, watching it on a terrible little black and white television with awful picture quality. But it was a remarkable thing to see, and I've been fascinated by that ever since. So getting a chance now to contribute in some small way to that is really a dream come true. And thank you again to Dr. Jiang for enabling that.
My name is Kelly Lu. I started working under Dr. Jiang around this summer. I spent the summer interning under him. I did some research, and it's been a really cool program, and I've learned a lot.
Hello everyone, my name is Tara and I'm being joined here today by Dr. Jonathan Jiang, Philip Rosen and Kelly Lu. Thank you all for being here.
Sure, yeah, thank you. Yeah.
Today we will be talking about the few of the most recent papers that you've all published, and they mainly discuss the Great Filter, extraterrestrial life, and the future of humanity beyond. And while the chronological order of the papers do not align with how we will go through them today, I thought that each paper formed part of a bigger story and a bigger narrative, and I took the liberty of kind of changing their time in order to go through them, in order to explain from the introduction all the way to the end, just as a way to form a story. And I hope that's okay.
Yeah, it's okay. Yeah. Feel free to ask any questions you may have.
Thank you.
Yeah.
So all the papers kind of go through almost 4 parts. And the first part is the introduction to the Great Filter and the introduction to the topic. The second one is the simulation of the important factors for the survival of humanity. And the third part is a projected timeline that goes from when do we reach the desired destination. And fourth is kind of a hopeful end to the papers is by talking about the beacon, the message we are sending into the galaxy. I would like to start with the introduction from the paper Avoiding the Great Filter, Extraterrestrial Life and Humans' Future in the Universe. Before I start, if you can please explain briefly what is a Fermi Paradox and how it's related to the Drake equation. I know I'm vaguely familiar with them, but it's helpful to put the two both together.
Right, and now Philip and Katie, you may add, and after I explain it. Now, I work for NASA and JPL since for more than 20 years. Okay, I still remember the first day when I come in and in the job orientation, and they explained it to be NASA vision. Okay, NASA mission. And one of the NASA mission is to understand, are we alone in the universe? is anybody out there, and who we are and where we come from. So this is always a big question. And JPL sent rover to Mars, okay, sent spacecraft and to visit planets in the solar system. One of the mission goal is to look for life, maybe ancient life, okay. So this is puzzles me for a long time, whether or not there's any other life outside the Earth, okay. Now the Fermi Paradox asks these questions. If there's any life outside the Earth, why not anybody contact us? Okay, that's complete silent. Now, think about the universe. It's more than 13 billion years old. Okay, there's hundreds of billions of stars in the galaxy, and maybe 2 or 3 trillion galaxies in the observable universe as we understand that. And given how big the universe is, and how ancient the universe is, why not there's any civilization developed before us, they can visit us as silent. So that's the Fermi Paradox. Now the Drake equation is try to come up with statistically to estimate, okay, if there's any life in the galaxy, how many? Okay, so many factors can be known. For example, the galaxy formation rate, the density of the stars, how many sun-like stars in the galaxy, okay, and how many planets for each stars. Many of this have already known, through the observations, through the theoretical considerations, okay. But there's other factors like what is the rate of embryogenesis, life appears, okay. That is largely we don't know, but we can estimate, okay. It's not zero. There's some published papers say, hey, and based on our current understanding of the physics, biology, chemistry, the rate should be and some numbers. Okay, there's a range, at least there's a range. And other things like how long the civilization can survive, this is we don't know. So in the previous publication, we can estimate, hey, if the how about our self-destruction rate is 0. If it's self-destruction rate, how about the 0.1%? What happened? This can be used computer simulations with the Drake equation and consideration. So this is part of, I should say, it's not completely finished. It's part of ongoing research. And maybe Philip, you can add some of your thoughts.
Sure. Well, first, although I have the privilege of working with Jonathan and his colleagues, I'm not a NASA or JPL scientist. I'm an independent researcher, retired from the energy industry. But very happy to help with this kind of study. As far as the Fermi Paradox and the Drake equation goes, so the Fermi Paradox, just to add a little historical background, is named for the famous 20th century physicist Enrico Fermi, who, in a conversation with colleagues in 1950 about extraterrestrial life, intelligent extraterrestrial life in the universe, he asked what sounds like a very simple but very deep question. He says, well, if there's all this extraterrestrial life out there, where are they all? Where's everybody? Why haven't we been visited or we picked up a signal or some other indication? And it's a question that scientists have wrestled with ever since. Fermi just kind of fleshed it out into very straightforward terms. One of those scientists is the late, great Frank Drake, who only recently passed away, and he formulated in 1961 his famous equation, the Drake equation, to try and get an estimate, a quantitative estimate, albeit with many assumptions necessary, of how many communicative alien civilizations might be in our galaxy. Communicative meaning they can communicate with radio signals, as we are able to do, but only relatively recently, in the last 60 or so decades, or 60 or so years, about 6 decades. So Drake came up with this equation in 1961, and it's been refined and improved since, but its basic form remains the same, and it's trying to answer this question: is there alien life? And if so, try to quantify it. The next big, I guess, change came, or step change in rationalization came in the 1990s when we began discovering exoplanets, planets beyond our solar system. And we have come to find in the last 30 years, with increasing complexity of instrumentation, such as the James Webb Space Telescope and the Hubble Space Telescope and other instruments, that planetary systems around stars are quite common. The solar system is not unique in that sense. Many stars, many different types of stars, have planets around them, but that's no guarantee of life on them. They can be too hot or too cold or gaseous or some other circumstance which does not allow, at least easily, for life as we know it. But because we found,
and also 5% of the planets is in the habitable zone.
That's right. We've confirmed over 5,000 exoplanets to date, with several thousand more candidates nearing confirmation. And again, with the new instruments, there'll be many, many, many more to come. And we're finding that a small but not insignificant percentage, maybe 5% or so, as Jonathan said, are in this Goldilocks zone, habitable zone around their host stars, where it's like Goldilocks is porridge, not too hot, not too cold. So liquid water can, with maybe an atmosphere, can exist on the surface in some areas, and with liquid water, the suggestion of life follows pretty quickly. So that's what we're trying to approach here, but there's still a lot of unknowns. That's a lot of approximations and estimates needed. Kelly, I'm sure you have some very good thoughts to add to that.
Yeah, I just wanted to look back at the Drake equation itself, which is, I mean, you could consider it flawed, just taking into account the amount of assumptions that it makes. Each of its factors, it seems, aren't really backed entirely by data. I mean, we have very little data on planets. I mean, we haven't even found any planets that could possibly sustain intelligent life so far. We haven't found any signs. So a lot of the paper and the ideas that we've put forth are mainly conceptual, as it is based on more of a conceptual kind of approach.
So I find that from the paper of the Great Filter, and the term, I think, is based on a previous paper by Robin Hansen in the 1996 of the same name, and it feels like it is kind of a resolution to the idea of where is everyone. Is that correct?
Yeah, we start to think about that, and based on, and in January 2021, I and my colleagues published a paper. After quite a few years of study, we try to estimate how many life in the galaxy, how many possible intelligent life in the galaxy. We run through the computer simulation, based on modified Drake equation. It's not exactly Drake equation because it need to update. And based on that simulation, it's very striking. The last parameter of that equation, and we call it self-destruction rate, is dominant. Okay, if we consider self-destruction rate is 0, there should be, long-lived intelligent life civilization in the galaxy. Okay, but it's very sensitive, because all the other parameters like star formation rate and even the supernova explosion rate, things like that, and they taking long time scales. Okay, and so once every hundreds of million years, maybe billions of years. Okay, but the self-destruction rate, at that time, if you check, for example, Doomsday's clock, okay, using Google, okay, you will find there's a website say, hey, and the percent and the probability to have a global scale nuclear war is 2%. Okay, in the peaceful time is 0.1%, something like that. It's not 0. So if we put that rate into the equation, we run the models, we will find the lifetime of intelligent life in the galaxy is largely shrinked, okay, largely reduced. So we tested, how about 0.0001%? How about 0.01%? Now, how about 0.1%? Now, if you're increasing that, you will find if the self-destruction rate reach certain numbers, no life in the galaxy is longer than us. No life in us. So this provides some answers to the Drake equation like grid filters. Okay, so for us, and so we are not able to reach for the stars yet, based on our current understanding of physics, our current understanding of technology. We are trapped on this tiny dot. Okay, and if we can reach other stars, maybe after 200 years, after 300 years, we can do that. We have a new understanding of physics, and we have a new technology. But I remember in 2016 when Steve Hawking was at Caltech, somebody asked, and Steve Hawking don't believe we can, and humanity have more than 200 years left. Okay, so that means the self-destruction is a danger, like climate change, like nuclear war, like pandemic, maybe artificial intelligence. It's quickly picking up. You can estimate, and so based on the data, how fast artificial intelligence can have an IQ, higher than human. You can calculate. Okay, so that add together, it looks like the things limit we reach for the stars is ourselves. Is a great filter ahead of us. So go back to Fermi Paradox. Nobody visited us. Why? Something stopped them to visit us. What is it? It's a great filter. So this is the idea. It's not come up all of a sudden. It's through our research. When you shift through the data, you think about that, do the computer simulation, it comes to some conclusion. Probably there's a great filter.
Yeah, I would like to quote one statement from your paper, and it's, quote, "The great filter has the potential to eradicate life as we know it, especially as our rate of progress correlates directly to the severity of our fall." Closed quote. If the great filter is a resolution to the Fermi paradox, it feels like we now have a new paradox, which is the more advanced we've become, the more is the probability of us doing a self-annihilation. And this is kind of the question that you might trying to be answer. You're trying to answer in this paper, as if, what is this thing that stopped anyone from contacting us now, and what did they have to go through that might have prevented them from reaching us today?
I see. Maybe Philip, I give you a chance. You can answer this question.
Yes, well, as our technological progress as a species has advanced very, very rapidly, the ability for self-destruction, unfortunately, comes with that. It's perhaps the price to pay. What I think of as a kind of window of peril opened up starting in 1945. If one was going to put a date on it, of course, that was when the first successful nuclear weapon was tested, and it's been open ever since, now for 77 years. The good news is we're still here. We're survived this far, about the span of a human lifetime in developed countries. Another example of complexity helping us as well is pandemics have happened before. The Spanish flu in 1918 is one historical example, and other times when pathogens have caused worldwide problems. But this time we fought back with very rapid vaccine development, and that has been wildly successful. Far fewer people have died of COVID than of the Spanish flu a century earlier, when vaccine development was almost zero, and technology-wise. So with complexity comes peril, but it also brings forth solutions. It's a bit of a race between the two to see which one takes the advantage. We can outsmart ourselves into destruction, or we can smart ourselves into the far future and continue technological progress, eventually making humanity more robust by spreading off-world colonization, be that the moon, Mars, or beyond. It's going to take quite a bit to do that, but if we want to become a species that is very long lasting, that in the Drake equation has a very big L, that is lifespan of the civilization. One of the best ways to ensure that is to become a multi-world, multi-planet species. So if something very terrible happens to humanity on one world, it can very well be avoided in other locations. And this includes disasters that are not necessarily ones that we cause ourselves. Of course, asteroid strike, comet strike, super volcanoes. These are things that can happen that we didn't bring on ourselves, but could have very destructive effects on civilization. Although it should be mentioned with asteroid, NASA, we really got to tip our cap to NASA with their very successful DART mission recently. Proof of concept demonstrated in the field of how we can defend ourselves. So there's another example of using our smarts, our very best technology, as a shield in this case, to avoid something that could annihilate civilization. And that's a way to think about it.
Kelly, do you have any input to add?
Yeah, I would completely agree with what Philip's saying. The point of that line was more of our growth is inevitable as a human species. Like, it's exponential ever since the Industrial Revolution. Things have just been really taking off. And it's more of a matter of, how we use and implement these new technologies or advancements that we're given. So, admittedly, of course, nuclear holocaust would be much more destructive than simply sticks and rocks. So it's more of how we end up using this technology that could correlate to how, how we fall from grace, is what that line is more about.
I'd like to add, the part of the reason we write this paper to publish it, okay, it is because of this, and so I remember in January of this year, and before we start to write this paper, I gave a seminar. After the seminar, the host sent me an email, say, hey, and what you said, you need to publish it. This will bring people awareness, to prevent the self-annihilation. It's a positive for us. So this is, and so if we're doing that, and so maybe in the future we can find solutions, and to this problem, we can overcome the great filters, as I hope.
I feel like there's also maybe a hopeful note to add, is that maybe everything is also relative. If we think about the great filter still before us, and we still didn't go through the self-destruction state that might have a destructive effect on the planet and on us. Maybe also the earlier transition from a single cell to a complex multicellular is also a great filter that we've passed. If we thought about that as a great filter and that no other civilization was able to pass through that, maybe this is also a hopeful that we have passed a great barrier.
Okay, so yes, you're absolutely right. The embryogenesis, for life to appear, not only appear, for life to evolve into intelligence is not that easy. Maybe there's a filter as well. Okay, but I think this way. I had a long thought of this, your questions, long before we start to think about these papers. Okay, you think about the Earth. The Earth is about 4.5 billion years old. Okay, it takes a long time for life to develop, evolve. Now, the first single-celled life may appear on the Earth 3.5 billion years ago. Okay, it took another billion years, perhaps, for that single-cell, simple life to become multi-celled, to populate some microorganisms in the ocean. Okay, it took another 500 million years, maybe hundreds of million years, for a little bit more complicated life to appear, It takes another few 100 million years for mammal to appear, for land life to appear. See, our ancestors walk on the earth maybe a few million years ago. It took a long time for them to learn how to fire, how to make fires, how to make tools. Okay, but you can see things gradually evolve, but the pace is getting accelerated. The modern language, the written language, communications may appear, let's say, 10,000 years ago, maybe 5,000 years ago, our written language. So civilizations evolved. Now, the language of mathematics may appear 1,000 years ago. Our modern science appears a few hundred years ago from Isaac Newton until now. Now, the technology, the electronics, the computers and iPhones, things like that, those radio signals, let's say, it happens about 100 years ago, 100 years ago, okay? Radio communication, radios, TVs. And I remember when I'm doing my postdocs in 1990s, we don't have iPhones, okay? We have a big cell phones like that. So it's getting accelerated. It's moving very fast. The pace of data, is moving fast. If you look into the future, you'll see we are accelerating into something. It's accelerating, maybe people call it, we are accelerating into a singularity. That singularity may be a great filter. We don't know it. Okay. In ancient time, when we have a war, we have a knife, we have we have a spears. Okay. Now we have a nuclear weapons. It's more efficient. So if you think of that, there's some filter ahead of us, perhaps, to prevent us to evolve further. But yes, there are some filters before us that took billions of years, okay? And we overcome these filters. But in the future, if any filter is coming ahead of us, and we won't have millions of years to overcome this, because it's accelerating of advancement of our technology and our daily life as well. Maybe Philip, you can add something around this thought.
Yes, our technology is indeed accelerating very rapidly. It's a terrible consequence of warfare itself. That warfare is quite the innovator, and development of the nuclear bomb is perhaps the most dramatic example of that, but certainly not the only example. There are good things that come out of that, like rocketry. We would not have had a space program that began in the 1950s and had spectacular successes in the 1960s and beyond if rocketry hadn't been pioneered during warfare and times just prior to that. But very high price to pay. But again, within all this complexity of technology that can be used for bad, there is technology that can be used for good and for the good to counteract the bad. So it's very complex. There's many, I guess you call it, waveforms that are superimposed on top of each other. If we were looking at this in a quantum mechanical way, it's complex, and we don't have any sort of guidebook to go by. We are the first technological species on this planet. We are the only one that we're aware of. To say that we're making it up as we go along is perhaps an oversimplification, but there's a little bit of truth to it, I think. But we can feel our way through. But what we do have is computational power that has been very rapidly developing as well over the last several decades. And we're able to model quantitatively circumstances that before were only sort of nebulous thoughts in the minds of researchers and scientists. Now numbers can be put to notions simply. And as such, we have tools. We've equipped ourselves with fantastic tools to better understand where we are and where we can be heading. And with that I think is where the solutions are, is to utilize our smarts to think our way out of predicaments, both self-created and also from without, from our environment.
I think this is a good segue to the second part of the story, which is the great filters that you've identified in the papers that might be used to self-destruct. Some of them are controllable within our reach, and some of them are not. I can list them as being the nuclear war, asteroid and comet impact, pathogens and pandemics, AI, climate change, and while it didn't have its own section in the paper, also unchecked population increase was also a major factor of the great filter. So if we move to the second part of the story, and if we start with the idea of the nuclear war, we know, based on the paper, we know how close we are, but also the only thing that is stopping us is probably still human wisdom at this point. But at the same time, the idea of the nuclear energy might be a solution in your most recent paper for the climate change, which is one of the other factors. So how do we reconcile the trade-offs between these different factors if, for example, in the nuclear war, the only thing is stopping us is like at least the barrier of the human wisdom is that stopping this kind of self-annihilation?
Yes, you're right. Just about a week ago, maybe 2 weeks ago, and there's an announcement, there's breakthrough in nuclear fusion. Okay, this ultimately can provide solutions, to combat climate change. Okay, and I think this is a good news. This is a good use of nuclear energies. Okay, but the nuclear wars, okay, although there's a human wisdom, but still there's hundreds of thousands, maybe there's thousands of nuclear missiles in the world owned by the countries. Okay, and although people had wisdom, how to through negotiation, but my take is this, because every year I look around, and you see every October's, okay, there's a military parade in China, okay, because October 1st. Every May there's a victory parade in Russia, and also nuclear, and there's parade in North Korea, so to speak. You look at that parade, those soldiers who step over the square, they carry weapons. Okay, those weapons are not for hunting; it's to kill humans. Okay, now there's trucks carry nuclear bombs, passing through. The problem is not with that. The problem is people. The problem, you look at those audience, those people watch the parade, they feel proud. They feel, wow, so powerful, so great my country is, But we don't understand why people feel proud. Aliens don't understand why people feel proud, because they are watching the weapons to kill themselves. So if you talk about the great filter, this is the great filter. This is a part of great filters. Now, if you talk about climate change, everybody knows climate change is a danger. Dangers to come. I attending a seminar just last month, people talk about plastic pollutions. Okay, plastic pollution, the microplastic is how dangerous to the planet. People know that, but people still use plastic. You see the keyboard, this one, they all plastic. People are not going to stop using plastic bottles. Okay, and there's dangers to climate change. We still drive cars because people think, oh, there's a danger, but I don't know how to do it. There's no solution. Politicians don't know how to do it. Then there's negotiations. So it built into our genes. People are not capable smart enough to solve it. This is the great filters. This is part of the great filters. And so this is, some good parts, some bad parts. People's mind, people's behaviors and people are unable to provide effective solutions. This is a great filters, I think. Yeah. Maybe Philip, you can add something.
Kelly, please do. Go for
okay,
it.
Kelly, yes.
Sorry. Okay. So, I believe that Tara, you called it human wisdom that kind of was like the breaking point, the split off between like nuclear energy and nuclear war.
I'm hoping.
Hopefully, let's hope that's a factor. But I would actually consider it more of a human self-preservation because it only takes so many nuclear weapons, like only a couple nuclear bombs, to set off an entire nuclear winter world war. The U.S. nuclear stockpile alone contains, I believe it's almost 4,000 warheads, just in the U.S. alone. So this kind of like militarization is what makes it very difficult for not only the governments, but the people who live in these nations to have very short-sighted tendencies, rather than like looking far into the future, how this is unsustainable. And it's the same thing for climate change. People just aren't looking farther. They think, oh, this problem, I mean, we can put it on the back burner, basically, because it's not going to hurt us, maybe not even our children. But that's the kind of mindsets that are problematic, especially when dealing with these kinds of issues.
I feel like I would like to go through the climate change in a bit, but before we go for it, I'd like to add something. After World War II, the advent of the atomic bomb, the world feels simultaneously became dangerous and also safe. Maybe because the powers realized the dangers of it, and they understood that what is the meaning now of everyone having the weapon to destruct the other. So, and then based on that, they started the global cooperation, like the United Nations, in order to contain any possibility of conflict. And as the president, Henry S. Truman, in the General Assembly of the United Nations, he said, quote, "If we do not want to die together in war, we must learn to live together in peace," close quote. And I feel like I agree with all that you're saying, is that there is a real risk with having powers using this. But I'm wondering if any power using this nuclear weapon to destruct others, it would, like you said, Kelly, it would be also self-preservation, right? Because you cannot launch a nuclear weapon without self-destructing. Is that correct?
Right. It's a sort of mutual agreement between nations is what's kind of withholding the peace so far.
Okay. And I'm glad you mentioned this, because there's another workshop I'm attending. Their presentation is about artificial intelligence. Okay. Now, the U.S. president had a box and had a briefcase. Okay. If you open that, you press the button, launch the nuclear missiles. Okay. I think many other countries' leaders may have this. Okay. But on that workshop, there's a serious debate, because president, no matter who he is, he's human. If decision made by him is likely to make a mistake, okay. Now, the best solution is to leave the decision to the AI, because the computers, it's better to do hundreds of simulations. In any situation, he have best decisions, how to win the war. Computers, through the simulations, it's like the computers is best players at the chess. He can win the world championship, the chess, okay, or the Go games. Okay, it's like the same. Now, on that workshop, I've heard the expert testified. And so when that moment happened, the US president don't press the buttons to rely on the computer to pass this code to the computers. The computer will calculate, will press the button, will determine where and when to launch the nuclear missiles, how to defend that. He had a better chance to win. If we do that, it seems like the human race, the fate of humans is relying on the computers. But it's the papers, and do prove that, and computers are better than human decisions. And now, I don't know in the future what's going to happen, but we have a large amount of nuclear aerosols weapons in the storage. how to deal with that. And yes, and so I just add some thought. I don't have solutions for that.
So this brings me to my second question: is that Thomas Sowell, a prominent U.S. economist, said there are no solutions, only trade-offs. And I think this is a good segue into the second factor, which is the climate change. I feel like the topic is polarized, maybe because we only speak in extreme solutions. And I feel like maybe the solution is somewhere in the middle, where, yeah. So what can you tell us about this? Kelly, you kind of alluded to the idea of people are not looking at solutions prominently, but what can we do about the climate change as a debate in order to bring everyone back to the center, in order to talk about trade-offs and not just solutions?
I think the purpose of our paper was just to do exactly that, was just to start a dialogue. If you could re-explain what exactly you meant by trade-offs.
For example, a trade-off would be one solution that would be proposed is to replace everything with a renewable energy in order to use using renewable energies in order to address climate change. But maybe a trade-off would be using a cleaner fossil fuels, for example, like natural gas, until the technology is developed enough that any subsidies for this technology are measured and calculated and do not mean that it's more expensive energy power to people who cannot afford it. So it's kind of, yes, we cannot let go of the fossil fuels entirely, but maybe a trade-off would be just a compromise until we get the technology to where it needs to be. This is just one example.
I think trade-off and negotiation to find middle ground is good. It shows progress, okay? But it not eliminate the dangers, okay? The greatest danger of climate change, so to speak, is uncertainty. Is we don't know. It's like you walk around. There's a possibility there's a cliff, but you don't know when you are hit the cliff. You don't know. You don't even know where's the cliff. Okay, so based on the data, based on observations, okay, I'm not talking about climate models. Okay, based on the data, in the past 20 years, past 30 years, the global mean surface temperature increase is accelerating. There's an accelerating curve. Okay. Now, if you want to project into the futures, you put the current increase rate of greenhouse gases into the climate model based on the physics. You run it. All models to project the warmings. But the uncertainty is how much. Okay. Some model project 2 degrees, some model project 10 degrees down into the future. Well, the model uncertainties. This is understandable. Another question is, scientists believe there's a tipping point. After the tipping point, it run out of control of the climate systems. Okay, but where is the tipping point is still uncertain. There's uncertainties. It could be 2 degrees. Okay, there's a paper published by Science. It says probably 1.5 degrees or maybe 2 degrees in that between. Okay. But there's uncertainties attached to that. That uncertainty is danger. Okay, that uncertainty is the danger. You through the negotiation, maybe you can slow down the climate change, but maybe not. These uncertainties. So just this morning, and I gave an example. The humans, is like passengers or crews on a ship. Already left home, but we don't know where we are going. Okay, well, not only that, the ship is already start leaking gradually, and that ship is become crowded. Many people is getting sick. And people know that's going sooner or later the storm is going to come. But there's an uncertainty. We don't know when the storm is going to come. If the storm is come, there's a possibility the ship is going to sink. So this is what we are now. Okay, and this is we are facing right now. Okay, so this is the uncertainty of climate change. Of course, people say, hey, the chances of that happen and is low. Okay, scientific community, majority of scientists believe it's going to happen. But let's be conservative. Let's say the chances the climate change will reach the tipping point to bring disaster to the human civilization, the chances, let's say 50%. I myself believe chances may be 50-50. Let's be more conservative. Let's say the chances is 5%. It's low, right? Think about that. You go to the airport, you buy an air ticket. If somebody and the ticket agent tells you, hey, sir, this airplane had a 5% chance to crash, you are scared. Okay, you are not going to buy this ticket. Now the climate change scenario is this. Nothing going to happen in the next 5 years. Okay, in the next 10 years maybe. But something, there's a possibility something is going to happen. The tipping point may be reached in the next 100 years, in the next 50 years. So this is the danger. And whether or not this is exactly going to happen or not happen, we don't know. So the danger is we don't know. That is the danger. That is uncertainty. Nobody on both extremes, nobody can definitely say, hey, it's going to happen in the next 50 years. Nobody. That's the danger to the humanity. It's like that ship. When to sink, we don't know it. But there's a danger. And the danger is getting bigger.
But do you think that maybe the Western civilizations are able to have this conversation because they have reached a level of advanced technology? They are advanced technologically enough to be able to transition and subsidize into cleaner technologies. But the same thing cannot be said for other countries who are also trying to become richer faster. And in order to get people to care about the environment, they need to be rich enough in order for them to care. And I agree that maybe one
what
solution...
you said is
Sorry.
What you said is exactly true. And 5 years ago, my postdoc and I published a paper. We illustrated, okay, and the air quality in the Western world, Europe, US, is improved a lot. At the same time, the pollution levels and in developing countries like China, India, is skyrocketing. Because of that, you already produce some perturbations in the jet streams, because the jet stream is based on the temperature gradient. Okay, now the Europe, US, Canada, they cleaner. The mid-latitude getting more polluted. You provide a ship to the jet streams, you'll see more extreme of that. Now, I remember in 2016, there's United Nations discussions about that. There's some sort of negotiations. Country like China, they will say, hey, based on the past 100 years average, okay, the US released huge amount of CO2. Only in recent years, they're getting better. Why not us? We want to develop. Okay, this is another great filter. Okay, because the human behave like kids. Why not? You're better. I want to be better too. And it's like a husband and wife is fighting. They only look at the other's shortcomings, not think about others. It's all the two kids. You're exactly right. This is very hard on the international state to have negotiations. That's why the rich countries should provide some maybe economic aid and something like that to the poor countries, maybe through that international collaborations. But this is also hard. And that is also a filter of us. Yeah, maybe Philip, you have more thought of these questions.
Yes.
On the international state.
Well, drawing a little bit from energy industry experience. So you mentioned transitions, Tara. That is very seemingly the way to go. Crude oil is easy once you find it and surface it. It's awfully easy. It's easy to transport. It's easy to use, and you get a lot of energy out of it. It's easy to contain, and it's got a high energy density to it. The hydrogen to carbon ratio in crude oil is roughly two hydrogens for every carbon, approximately. Natural gas produces much less CO2 per unit energy, and its hydrogen to carbon ratio is 4:1, or hydrogens for every carbon. What is this telling us? Hydrogen is our friend. Hydrogen is the good guy in this whole energy equation, and that points very directly to natural gas being the ideal transition. Now, we have on Earth plenty of natural gas. We're not going to run out. Right? We have it all the way through this century and deep into the next century. We also have a lot of crude oil. We're not going to run out. The world has started out with about 4 or 5 trillion barrels equivalent of oil, and we've surfaced about and burned, oxidized about 1 trillion since the 1850s. But there's plenty more there. That's good news and bad news. It's relatively cheap, easy energy, but it does bad things with CO2 to the atmosphere. But again, we have this transition, fossil fuel, natural gas in abundance, and it can be transported almost as easily and used easily as well. We can make electricity with it. We've known how to do that for a century or more. So that's one of the very obvious answers in terms of natural resources that are fossil fuels. But as well, we're ramping up on renewables and green energy such as solar and wind. The technology there has advanced rapidly in the last couple of decades and brought down the unit cost of that. There were wind farms and solar farms decades ago, but they were not very cost effective. So they didn't get done so much. Now there's support for more of that, and that is another way to go, as well as nuclear. Although there's some safety hurdles that still, and public relations hurdles that still need to get passed on that. But transitioning is going to be the key here over the next several decades to stay under the tipping point, as Dr. Jiang mentioned, for temperature rise. The temperature has risen. It's going to rise a little more, but we haven't tipped yet. That's the good news. Where exactly, how much further we have before we do tip, that's the uncertainty that Jonathan has touched upon. And to stay away from that, to continue having a safe enough margin between where we are and where that tipping point is, whether that's at 1.5 degrees C or that's at 2 degrees C or something else. The transition has to happen and has to be aggressive. It is happening. That's the good news. It is happening. It needs to happen more aggressively, but not leaving behind people and their lives and their livelihoods and their families and their safety. When people lose security, when the lights go out, when the heating shuts off, folks get very desperate, and they're not going to care very much whether their energy is restored through oil or coal or natural gas or nuclear.
Or burning trees.
It's not going to matter. It's just get the lights back on, get the heaters going. It's cold in here. So we don't want to trigger that because we'll regress. The progress that we've made can be threatened by a regression triggered by being a little too hasty and not making good decisions at each step. So it's really threading the needle. It's going to be tough, but it can be done.
But this is where my question also, I wanted to ask you about, when we speak about renewable energies, wouldn't also the trade-off is that we will have to do lots of mining to extract the material required in order to do the renewable energy? I mean, the conversation usually happens when after we do the wind turbine, but not the process that makes the wind turbine itself. And I'm wondering if extracting fossil fuels would be less or more devastating on the overall environment than mining for all the material that goes through a wind turbine or a solar panel, or what do you think, Dr. Jiang?
And I'll pass this answer to Philip because Philip had more experience in terms of energy use, right? Yeah.
Well, I'm from fossil fuel industry, so we get into a whole lot with building wind turbines or solar farms, but there's a little bit of background there that is generally gleaned from the literature. And yes, you got to do a fair amount of mining to get the minerals, to get the metals that are particular for these installations. But again, the good news is that once you get it all built, it'll last a long time. Wind turbines have a lifespan, and then they need, like any other mechanical device, certainly rotating equipment, you got to replace it eventually. You got to service it, you got to replace it. Solar farms, solar panels are not eternal either, but they will last a long time. But there is mining involved. That's something that cleaner techniques for mining need to be found. And this ties back in with the use of fossil fuels themselves. When you oxidize a hydrocarbon, when you burn it in the atmosphere with oxygen, and you oxidize the hydrocarbon to all the way to CO2 and H2O, the H2O goes in the atmosphere, you don't much care about it. The CO2 is the problem. CO2 capture technology, CO2 carbon capture and sequestration, is a rapidly developing technology as well. So here, yeah, you're going to make the CO2, okay, whether it's through mining operations or refining operations or power generation facilities or something else. If you're oxidizing hydrocarbon, you make CO2. But rather than just tossing it to the sky and letting the CO2s float around for a long time, CO2 persists in the atmosphere on average a little over 100 years. It's annoyingly unreactive. You capture it, you grab onto the CO2s, and you take them away, bury them back in the ground. That's the sequestration part, basically burying it back in the ground where the carbon came from. And it's not going to cause any problem down there. It's on the ground, it's not in the atmosphere, it's not a greenhouse gas. The carbon's back where it essentially belongs. So there are other ways of approaching this where we can still have at least part of our cake and eat it, if you will, and be able to do the mining and even continue utilizing fossil fuels to some extent while not suffering the full effects of CO2 into the atmosphere.
In a paper published in Nature Climate Change, it has shown that, like you said, CO2 has kind of been captured because Earth has been getting greener over the past 30 years. It said that as much as half of all vegetated land is greener today, and only 4% of the land has become browner. So is the CO2 capturing would also include maintaining it to a degree that it would at least be useful for the plants to stay green? Because if we captured all the CO2, wouldn't this mean less food for the plants?
Well, yeah, it would be quite remarkable if we had such a capacity for carbon capture and sequestration that we actually were in danger of a atmospheric CO2 scarcity. I think that might be a pretty good problem to confront. We just dial down our carbon capture and sequestration facilities. We twist the knob a little bit counterclockwise and dial her down. We have to have that capacity at first. But it's a good point. If you put more CO2 in the atmosphere, plants feed on that, so there's more robust plant growth, and that's helping. But we cannot rely on that to be a kind of thermostat, if you will, on keeping CO2 in a safe range. We're we've been putting it into the atmosphere quite rapidly since the start of the Industrial Revolution. We're getting a little bit better about it in very recent times, but that trend we need to continue to attenuate and do it by all the above approach, meaning going to cleaner burning fuels and carbon capture and sequestration and energy sources again that do not involve any CO2, solar, wind, nuclear. We've pretty much tapped out all the rivers for hydroelectric, unfortunately. That's an awfully easy way to go, but it's tapped out. But there are still some further, and of course there's the hope, at least some decades from now, of the big prize, which is nuclear fusion, which there's been a dramatic bit of progress on that very, very, very recently. However, that's still, honestly, probably decades away from being able to be scaled to industrial scale application. It's in the lab, and it's going to stay in the lab for at least a little while longer.
So for the second, I don't know if any of you would like to add anything to the climate change debate.
Well, and my student and I just published a paper, I think, about a week ago, okay? And it analyzed the observed data and the climate model projections. And so we are going to reach 1.5 to 2 degrees within the next 50 years. I mean, the global mean temperature increase, okay? We don't know that's the tipping point. We don't know yet. But as a paper published by Science, they argue 1.5 degree is likely to be a tipping point.
When you say a
tipping point means something.
Yeah, sorry. Yeah, I wanted to ask
you
what it means.
Yes. Okay. And tipping points mean when the global mean temperatures reach that degrees, okay, and some more rapid change in the climate system, weather system, is going to appear. Okay. Some of the change may be irreversible. Okay. It's like you go to a state. Okay, you cannot come back. Okay, so that's the tipping point, and in turn, maybe will be all of a sudden you will see more frequent and extreme weather. Okay, and maybe hurricane or typhoon or jet stream is shifted so severe, or it will trigger, the heat waves, well over human can experience. Okay, something like that. Okay, that's the tipping point. Or the Arctic, maybe Antarctic, and ice melting, and ice cap melting will be accelerated.
Yeah, I think I've read this paper. Is it? It was published recently. It's called "The Avoiding the Great Filter: An Assessment of Climate Change Solutions and Combinations for Effective Implementation."
Okay, it's not a paper, and it's a paper published by Earth and Space Science, and published by Earth and Space Science, and about years ago. And if you search for there's a science paper published in September this year. You search 1.5 degrees Celsius and tipping point of climate change. You will find that paper. Okay, that paper is by another group of researchers, not me. Okay. Mm-hmm. And our paper published a week ago in Earth and Space Science is called 21st Century Regional or Global Surface Temperature Projections. Yeah.
Okay.
So something is going to happen, and in the paper we cannot definitely say this is the tipping point. No, and we just illustrate based on the current data, the best climate model projections. Okay, 1.5 degrees warming globally is going to be reached within the next 30 years. If you look at all the climate model, the best climate model the nation has, it is going to come.
Yeah,
we certainly will have a 3 degrees by 2100. All models, it's not just one model. Okay, that's represent the best mind on the earth. Okay, they have developed models, they run the models, check the model with the observations, best understanding of physics, and it's going to reach. And people can say, hey, I don't believe that. It's fine. It is fine. But this is the best climate model developed by best mind, best scientists on the earth.
I think it's hard to dispute the fact that humans have contributed to the climate change, and that climate change is going to be a problem. I think maybe the discussion is more of what solution can give us the best, most efficient, and the most benefit on the long run without having it to be so costly, or without making people have to pay more for energy. I think this is probably where the conversation is which solutions will provide the best benefit on the long run might be a good question.
And now people talking about recently is nuclear fusion. Okay, this will, without that, all the other things you're talking about, the solar panels and wind powers, it will not power the aircraft you fly from Los Angeles to New York. Okay, you fly the aircraft, we need fossil fuel. Okay, and so there's no effective solutions, economically cheap solutions to that. Of course, if money is not a problem, okay, let's build a gigantic solar plant field in space. Okay, let's cover all the world desert by the solar panels. Maybe we can largely solve the problem a little bit. Okay, the DART missions to defer asteroid, and Philip just mentioned. Okay, it's just a preliminary experiment. And so scientists had a plan, say, hey, we can develop this technology, implement this type of technology in space in order to divert all the asteroids' income, but it's too costly, no money. And but this is another great filter. I tell you why. You see, early this year in January, Biden administration released a budget. The money is going to use to develop weapons to kill ourselves, to preparation for the war. So-called military budget is $800 billion. Okay. NASA budget $25 billion. Okay, and so if you want to develop something to defer the asteroid, develop solar panels in space, how much? If you say that is $1 billion, too costly. Congress is not going to pass it. This is the filters we have, and so the limitation for us to develop anything to prevent ourselves, and you can say it's money, but actually it's our behavior, our children's thinking, and our short visions, not long visions, that stop us to do that, in my view.
Yes, I agree. For example, maybe one behavior does contribute a lot to the conversation. For example, we can avoid lots of loss of lives if we did proper zoning and regulations around coastal areas.
Yeah.
Something very simple, but very effective on the long run, and it's largely dependent on human behavior.
Right. Yeah.
So if we shift gears a little bit and we talked about the artificial intelligence, and I'm curious to hear your thoughts about this, because for me right now, artificial intelligence is only within its computational power, and it's only residing almost in a computer format, like from a coding perspective. But in order for the artificial intelligence to reach the destruction of human civilization, wouldn't it need the physicality to act out what it finds?
Okay, so my understanding is this. Last time I talked about, I discussed with a manager, with my friend at Google. He works at Google. Okay, he talked about this. One day he was watching, a few years ago, and they want to test the IQs of AIs. Okay, AlphaGo, for example, and the machine that beat World Go game championship. Okay, the IQ he told me is about 61. Okay, something around that. Okay, now the IQ of my neighbor's dog, he always told me that dog is very smart, and maybe the IQ is 20. Okay, humans are smart. Humans IQ maybe 100. Okay, people like you maybe 120. Okay, how about Einstein? Einstein's IQ 150. And now the computer speed is getting increased, and also the information storage is getting increased. Okay, the expert believe there seems to be no limitation of the future growth of the IQ for the AIs. Okay, quantum computing technology is developing. Okay, think about that. In the future, there's an AI's IQ is 500. Or the IQ is 10,000. In theory, it may be possible. Okay, especially and right now there's a machine learning technology. Okay, machine can learn by itself through billions of simulations. He can learn it. The IQ can be increased. Now go back to that dog. Humans are more superior than that dog. How about the ants? The ants' IQ may be 10. If you see an ant, we just squeeze it. And so imagine in the future, based on the current speed of technology increase, it is possible that AI's IQ is more superior than us. Whether or not there's a danger to human, we don't know yet. Again, these are uncertainties, but these are possibilities. So this is why people talk about the danger of AIs, including Steve Hawking. He said maybe AI one day will destroy us. And maybe Philip or even Kelly, you can have some thoughts along these lines. Yeah.
Okay, Kelly, please.
I don't really have much experience in AI. I think it's just kind of an up technology that's just another one of those things that we have to be careful about how we use it. As with all the other advancements that we've made, it's not an exception. I think it's just something that could potentially be very helpful and useful, but it could also be extremely, extremely dangerous for us as a civilization.
Yeah, so that's why when I listened to that workshop about who control the nuclear aerosols, press the buttons, I'm a little bit scared because human had emotions. Okay, even human know this is wrong. Sometimes humans still do it. Okay, AIs don't. AIs may take action based on this is correct, this is wrong. Okay, based on this is correct. Okay, and so, for example, to salute world hunger, for example. Okay, AI may say, hey, kill half of the people, then anger problem solved. Okay, you see, this is Space Odyssey 2001. Okay, the whole. Okay, and his mission is mission success. He don't care to kill anybody. Okay, he don't care to kill anybody. So, so that makes me think about that. Yeah.
But it also depends on who programs it, right? Like if it was programmed by...
Okay. Yeah. Right. Okay, right. You're absolutely right. But there's a new technology. Okay, you develop a program, the machine can learn by itself. For example, AlphaGo. I go back to the AlphaGo. No programmer to tell how you win these games, but the programmer gave you procedure. Okay, which procedures? Okay, you prove can win. Then AlphaGo can learn by itself through millions of simulations just by themselves. That's called machine learning. Machine learning, there's a procedure developed by humans. You install on the machine, follow this procedure, he can learn by themselves. One day, maybe, okay, he's smarter than you. You say, oh my God, I want to switch off switch you off. Before you switch off, he already has a solution to prevent you switch off. And that's the danger. Yeah.
But
And
you mentioned, I'm sorry, Tara, you mentioned about being able to act. So
yeah,
if an
the
artificial
hardware.
intelligence, exactly, if an artificial intelligence is basically contained inside a black box, sitting on a shelf, or sitting in a lab, it might communicate some interesting and peculiar things, but can it really make those actionable in the physical world? It's a good point, and that's where hooking in computers to our actionable systems, in the most extreme case, nuclear weapons, we have to step into that very, very carefully. Of course, in popular culture, this has been explored. War Games, what was it, movie 1983, I think, was one treatment of that up on the big screen. But and as Jonathan mentioned, 2001: A Space Odyssey, a favorite of mine, going back to the 1960s by Arthur C. Clarke, where the computer goes a little nuts for some very unusual reasons, and starts killing off the crew, but doesn't think it's really doing anything wrong. We have to be very careful about who programs it. That's correct, and programming in if the computer, if an artificial intelligence really is intelligent and not merely artificial mimicking, but is truly an intelligent entity, we'll call it, then it stands to reason that it would have a grasp of morals and ethics, as we do, as humans do. Some of us maybe a bit more so than others. But our best people in ethics and morals and in good foundational principles need to be involved in the programming so that what we create is benevolent and not malevolent. Because
that's right. Yeah.
To its own devices, quite literally, we don't know which way it would go. It could be a good thing, or it could be, to use another movie analogy, of course, the Terminator. We don't want that. So we have to be very careful in how we program it, how we design it, and what we connect it to make it actionable in the physical world, in our world.
And I would like to add to that even when we connect it to something, we have to make sure that it's not hacked by anyone who would actually also change the code somehow in order to make it do whatever they need it to do.
Yes, and that's maybe one of the biggest challenges of all, is that you can get all of the best, most benevolent, smartest people in the room to build an artificial intelligence and make it wonderful. But as we've seen, there's just about any system can be infiltrated with enough cleverness, enough malevolence in this case. Somebody can get their way in there who's bad and cause it to do bad things. This takes the form in daily lives, most people's lives, of having their credit card hacked, and well, you start seeing $985 jewelry charges show up that you didn't make. This is unsettling.
That's right,
But it's an annoyance, but it's not going to bring the world down. So we have to make systems so thoroughly hardened against malevolent intent that it can't. This is building in fail-safes. Gosh, here I go with another movie analogy, 1964, Walter Matthau. Fail-safe, which explored this topic, a long time ago, where how do you build into a system the protections such that if multiple failures happen, you don't get a calamity. And we deal with this in the energy industry on a more pedestrian level with our complex processing facilities, chemical plants, and refineries. We have to figure out, it's required by law, by OSHA, Occupational Safety and Health Administration, to think up every scenario within reason that can go wrong in a plant. And then what are our countermeasures? What are our safety systems to prevent that or to mitigate it if it does happen? What's the probability? It's risk management, probability, and severity of the event if it were to happen. But there are safeguards that can be built in just as they're built into industrial systems, and they work pretty well. Not perfectly, but pretty well. Such safeguards need to be taken very seriously when building artificial intelligence systems. And with the default being, if something goes wrong, shut it down. Go back to manual, shut it down. That's what industrial systems do. If the automatic system fails, it senses the failure, and it disengages, and humans go back to controlling it until things get straightened out. Again, it works pretty well at that level.
I am concerned a little bit about this because I just would like to follow up on your point. I agree with you. The idea, for example, COVID, I understand that we were able to avert the disaster of COVID by probably rolling vaccinations very early, and probably would have had more success if we did early treatments that would be able to save even more lives than just the vaccines alone. But also, if we think about it, and this is also one point in your paper about pandemics, and the idea now that more hypotheses are supporting the theory that COVID started, regardless of how it escaped or how it moved itself into a human population, it actually started, the hypothesis, strong evidence says that it started from a gain of function research. And this is where the idea that they actually might have made the virus so much harder for the good intent to make it possible for us to treat it, but then it also made it harder for us also to treat it, because it made it so much more deadly. And right now, instead of shutting down gain of function research, there are proponents that we should do more labs to allow for more gain of function research projects. So this is also falls right back to your paper about that.
Yeah, this is very hard questions, and I don't have effective answers to that. Philip, you have answers, or Katie?
Well,
Yeah, it's probably more rhetorical.
Right. Okay. Yeah. Mm-hmm.
yes, but it's tough. We again, using an industry analogy, if you go back 100 years ago, 80 years ago, 100 years ago, facilities that processed oil were very, very simple. Simple distillation, that's it, you're done. And most of the resource got thrown away. There's not a lot that can go wrong in a facility like that. It's just a very simple creature. But as the decades went on, population increased and energy demand increased. Everybody's got a car in their garage now, and everybody's got a garage to put it in. There's a greater capacity need. So you got to dig deeper into the barrel of oil. You got to refine more complexity in the plants, and thus more things can go wrong. The more complex you make something, the more that can go wrong in systems. However, within all of that, complexity and robustness of safety systems also increases. Again, it's sort of like it's like a competition, like a race between the bad side of technology and the good side. This goes back to what we were talking about a little while ago, nuclear war and other topics. We're in a race here with ourselves. And we have the capacity to have it go in a bad direction, but we also have the ability to keep it within the guardrails. And that needs to get maximized, that capability, so that we do it, but we do it in as safe a manner as possible. And nuclear energy is another example. There were accidents that happened years ago, and even in the last 11 years with nuclear power facilities, but they are safer now than they were back in the mid-'80s with Chernobyl or in times prior to that. And we don't abandon it. Because there's an accident, like a 3 Mile Island in 1979, Chernobyl in 1986, or over in Japan in 2011 with the earthquake and tsunami there. We not say, don't abandon it, make it better.
Right.
Learn from lessons learned and build better safety systems.
Right. There are actually, I agree with, it's two sides of a sword sometimes you think about that. It's competition, okay? The technology can make us safer, but at the same time, technology may impose danger to us. One of the paper we published, we estimate based on our current trend, and so it's likely we can reach type 1 civilization by 2370 around that times, okay? Now, on another paper, because of technology advancement, and so we may like to destroy ourselves, and in the next 200 years. Okay, so there's a race. Okay, and maybe we can migrate to the Mars to other planets in another 100 years, things like that. So it's a race, and part of the reason to the race, I think the humans. The question like that you answered, we are limited by our intelligence. Go back to the dog again. The dog is very smart, okay? But no matter how hard you teach the dog will never understand the Earth moves around the sun. The moon moves around the Earth because his IQ is limited. Humans are very smart, okay? Smarter than the dog. But there are some things we never understand. We don't have solutions because we are limited by our brain powers, by our IQs, 130. Yeah. So some of the questions we don't have the answer. We are limited by our intelligence. Things like that. Yeah.
So I'm happy that you talked about this paper, because this takes us to the third chapter of the conversation, or the story that your papers is trying to tell, which is the projected timeline for human expansion. And if I may summarize briefly for everyone who is listening, what the paper is about, and please correct me if I'm wrong. The basic premise is that the paper attempts to project the earliest possible launch date for human crewed missions from cislunar to selected solar system and interstellar destination, but using that logic that such an endeavor and development and technological advancement is directly correlated to the computational power, which is then directly proportional to the transistor count per microprocessors, on which scientists are relying in order to advance, scientists and engineers, in order to advance their ability to make engineering systems that will get us there. Is that fair?
Right. And actually, to the listeners, my co-author Philip come up with this idea first. And so Philip, you have your comments here. Maybe you have your more comments here. Yeah.
Perhaps a little bit. So I was thinking about expansion, human exploration. We've gone to the moon and briefly landed some astronauts there, and serious plans are in the works for humans to Mars. But with that, I got to thinking, well, what are the parameters that are kind of overarching on our progress? And one of them, certainly not the only one, but one of them, which turns out to be rather quantifiable, is computational power. And that is related very closely to how many transistors we can get on into a microprocessor. And this, of course, is exponentially grown over the past several decades. There's very famously Moore's law, which says that this number doubles about every couple of years. I think it's every 2 years or so. And then I got to thinking, well, all right, transistors are somewhat analogous to the synaptic connections in the human brain. So our brains are still much more complex than the most densely transistored microprocessor at present, a couple of orders of magnitude more complex. So these chips still have a ways to go, but they're catching up. And I thought, well, if we play out the trend a little bit, if we let those curves go into the future, we utilize that to make some projections with the assumption, and it's a big assumption here, that we needed another data point. We know we landed humans on Mars back starting in 1969. Make an assumption that we'll get the first human boots onto Mars in perhaps the late 2030s. A little bit ambitious, not hugely ambitious, perhaps, timing. So if we know those two data points, and then we put that against our computational power curve, which is continuing to increase, then what crunch the numbers together, what does that project? What it projects is that we can go further out into the solar system in the decades beyond that. Asteroid belt, moons of Mars, moons of Jupiter, and beyond that, Saturn. Interstellar which will be quite a ways off, But that coming back to survival of humanity and avoiding the Great Filter, that's how you guarantee your existence. Is don't put all your eggs in one basket. I'm quoting from a quote, and I'm embarrassed to say I'm forgetting the author of the quote. But don't put all your eggs in one basket. Have multiple baskets. So if the one basket develops a hole, well, it's okay. You got some in another. And that other basket may be Mars or elsewhere. Don't even confine yourselves to just Mars. So we have this future if we are clever enough or wise enough to grasp it.
I wanted to sorry, Dr. Jiang, do you want to add anything?
No, it's okay. And yes, you can ask questions. Yeah, that's right. Yeah, go ahead. Yes.
I was curious as to, I looked at your paper and it was actually fascinating. The concept was really interesting. And I'm wondering if there was a paper or an article that I read, or rather a paper by Yasushi Sato called The Reliability in the Apollo Program, in which he discussed the balanced approach between reliability and the engineering judgment. And for example, he noted that there was 100 Atlas missions launched before John Glenn went into orbit. And the reason I'm asking this about the reliability is whether these numbers include the reliability, or it includes just the successful attempt of launching a crewed mission, or does it include all the other trial and error in order before we send humans to anywhere?
No, on that paper we didn't include. It's a simple calculation, simple model. We didn't include that reliabilities. And that said, I still trust our prediction is more or less along the lines. Okay, you think about next 50 years, it's going to happen. And a month ago, NASA successfully executed Artemis 1 missions. Okay, so by 2028, NASA had a plan to land astronauts on the moon. Then there's a plan to start to build a moon base. Okay, by 2038, the astronaut is going to land on the Mars. So people like Katie, when she graduated from the graduate school, let's say, and once she grown up, she will experience that transitions. We are moving outward and into the solar system. It's going to happen within 100 years, within the next 100 years. Yeah, I think so. Yeah.
I think that what was most fascinating as a note in your paper is that how significantly small is the jump between a flyby mission and a robotic landing, and the big jump between a robotic landing and a human landing. It was from about 10 years to over 300 years to make this jump. That is a long time.
Yeah, it's a long time, and that's due to a couple of factors. One is the complexity. We humans are, space is not a very friendly environment. There's nothing to breathe, and there's a lot of radiation, and it's either too hot or too cold. So we humans are very fragile creatures. We need a lot of shielding, a lot of plumbing, a lot of other atmospheric supports, if you will, environmental support to carry us even for a modest amount of time, a couple of months, 6 months, 6 or 7 months to get from Earth orbit to Mars orbit. So that's a big complication there. The other one is a tolerance for risk. If a robotic probe goes off course or crashes or something happens to it and we lose it, well, it's an expensive piece of hardware. That's all it is. And we learn from it. We go build another one and try again, being a little bit smarter as a result of the lessons learned. If we lose, heaven forbid, astronauts, that's a whole other creature there. Then that slows things down greatly. And there's a lot of reassessment there and a lot of kind of soul searching that goes on. The Apollo project was moving forward rapidly in the mid 1960s, and then in the early 1967, there was the terrible tragedy of Apollo 1. The first 3 astronauts we lost were there in Apollo 1. And that caused a lot of delay. We didn't get back on track until Apollo 7 went into orbit, and then Apollo 8 circled the moon at the end of 1968. So it's something that has to be gone into very, very carefully when humans are involved. That's why you see a big delta. The other thing is infrastructure. If you're going to go and like Apollo and land on the moon and stay there for some number of hours or a day or two, and then come on back to Earth, you don't need a lot of infrastructure there to greet you. You can just bring it with you on your lunar excursion module. However, if you're going to land astronauts on Mars, say, they're not going to pack up and leave a day or two later. They're going to be there a while. It's the orbital mechanics, if nothing else. The launch window only opens up every about 26 months, from remembering right. So we've got to put a lot of infrastructure there, basically a habitat there in place ahead of time. So we're gonna have to build out our human expansion network, our human expansion web first with robots. We've already begun to do this. We'll have to do it more so. We're going to send the robots out first, and they're the ones that'll prepare the way for the humans to be able to make a landing and remain for an extended period of time, and also get back if there's a return journey involved. And that's again something that if you're only going to be on the moon a very short time, measured in hours or a few days, you don't need it. But if you're going to be there longer or go further out, you're sure going to need it.
Okay, that's not right.
But I think it will also take, based on your projection, how long do you think the jump is also between successfully landing humans and actually landing them, like you said, with an infrastructure that is enough that if everything goes bad on Earth, they're able to sustain themselves completely autonomously?
Yeah, you're talking about robust colonies where the colony can maintain itself independent of any assistance from Earth. That's further down the road. The paper that you've referenced there is just first successful human landings. Get a pair of boots on the surface. Bang. That's a successful human landing. But as far as a robust colony that's sustainable, you would need all the environmental support, and you would need genetic diversity. I've read where that number is at the low end, it's about 100 to 150 individuals if you want to have sustaining generations survive. And that's again, that takes us back to greater infrastructure that's going to be needed. But the progress is being made there. We're putting rovers on Mars repeatedly, and they're semi-autonomous, and we're learning the conditions there, how to survive on a place like that, where there's only a very thin atmosphere and it's mostly CO2, and there's a lot of radiation. But we're learning with those rovers, and they're teaching us quite a bit. So we're on our way, and as Dr. Jiang mentions, Kelly's generation is going to be the one that's really going to see this really pick up speed rapidly. just as the generation that came of age in the 1960s were the witnesses to Mercury and then Gemini and then Apollo. Kelly's generation will be the witnesses to Artemis and what comes after that with Mars.
That's exciting, Kelly.
That's right.
Bring the popcorn. It's going to be a great show.
That's right. Bring popcorn. Yeah.
So my last question about this paper is, can you speak to us about what possible breakthrough technologies are needed right now by, for example, the private companies or corporations like SpaceX or Blue Origin, with the help with the of course mainly NASA and all the space agencies around the world, in order to make this happen? Are we talking about probably different propulsion systems or just more advanced version? What do you think?
Okay. My understanding is, and people talk about the propulsion systems, solar cells, and ion propulsions, even the nuclear powered propulsion systems. And I believe myself, one breakthrough we needed is breakthrough in physics. Okay. Our current understanding of physics still, no matter what propulsion systems, and it limits us to reach for the stars. Even for the star closest to us, 4.3 light years, even the most advanced propulsion system I can think of, if you reach there, it needs thousands of years, and fast, of course. And our technology is accelerating very fast, and so I think this question ultimately, and I cannot answer that. Maybe Kelly's generation, you can answer that. When you're grown up, you'll have the answers. And right now, I'm just one of the crew members on the ship. We don't know where the ship is going, and the ship is in danger. That's it, And maybe Philip, you can have more answers of that about private industries. What is we needed?
Well, there's private industry is really coming to the fore, and this is something that wasn't there during Apollo very much. Everything was through NASA, and it worked spectacularly well. But we see private industry stepping up and seeing these opportunities. Some very forward-thinking folks are putting a lot of money in that direction. But as far as propulsion systems go, we are familiar with chemical rockets. Basically, you take a couple of reactants like liquid hydrogen and liquid oxygen, and you bring them together, and you react chemically very, 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 very rapidly, and you get thrust, and that moves the ship. But there's a limit there, and about the best you can do on nozzle velocity there is about 5,000 meters per second, I think. That's the limitation you run into with chemical reactions. There's only so much energy in a chemical bond, either breaking or making a chemical bond, and that limits how powerful your thrust is. So it's enough to get to Mars. We've demonstrated that repeatedly with landings of robotic probes there. You can get to Mars in about 6 or 7 months if you time your Holman transfer of it properly. But if you want to go beyond that, practically, more advanced propulsion systems are likely going to be needed. Certainly, if you want to go interstellar, you're going to need much more advanced propulsion systems to get you there faster, starting to get to a significant fraction of the speed of light, which we don't get close to now. We don't get close to with conventional chemical thrust engines. But there are technologies to explore there. The ultimate limit is still just the speed of light, which is awfully fast. And there's a lot of room. Yes, the physics. There's a lot of room to stretch our legs between where we are right now with chemical rockets and the cosmic speed limit, if you will, of the speed of light. And if we can even get to just 10% of the speed of light, then the nearest star is not thousands of years away. It's not hundreds of years away. It's 40 or 50 years away if we can get to 10% the speed of light. So we there's it's not beyond reach. It's a tough one, kind of like climate change and so many other things. It's a tough one, but we humans are pretty good at overcoming tough challenges.
I would just like to talk about the last chapter of the story, which is the beacon in the galaxy, the most recent paper one of the recent papers that you've published. So the story that we were telling was the great filter, making everyone aware of it, running down the factors that impact the human civilization, and then assuming we passed all that, we talked about the projected timeline for humans to expand further, hoping we resolve those major issues. And the last one is actually sending us, as having survived, to the galaxy. Dr. Jiang, I know that you've worked on this paper, so can you explain to us how is this different from the previous message that was sent in the 1974, the Arecibo message, and why it needed to be evolved?
Okay. The Arecibo message was sent in 1974. At that time, I was a little kid. Okay. And my father, I remember, he read something, I think it's from the Voice of America, that's radio. Okay. And, it talked about that. I still remember say, hey, and the Americans are sending this message. This is not correct because if they send this message to outside the Earth, it should represent citizens of the Earth. Okay, and that message should not be sent without agreement by citizens of the Earth. I remember that, and my father mentioned that. So when I grew up, and in 1974, at that time the only planets we know is solar system planets. There's lots of stars. People think, hey, there's a planet around other stars, but we don't know yet. Okay, and we beamed that message to the global cluster, and I was wondering, it takes maybe hundreds of thousands of years to reach the global cluster. Okay, when I grown up, especially in the past 20 years, so to speak, we discovered exoplanets. Now we have more than 5,000 exoplanets discovered. And also it relates to our previous research. We try to find out where in the galaxy is most likely to have civilizations. If it's too close to the galactic core and the density of stars too high, radiation too high may not be suitable. If it's too outside, the density of stars too low. Then in that research, we identified probably about 4 kpc, 13,000 light years away from galactic center. That's most probably the location, maybe plus minus 2 kpcs, that including us. So and also 1970s technology, we don't have internet yet. Now we have a lot. We have advanced internet and also advanced coding systems. Okay, and that message I believe is too simple. Okay, so I think it's not recently, since I was in the graduate school, I think when I grown up, when I go to the workplace, I will redo the message, So that's why, and we want to do this, and we also want to write up this message to remind people we are citizens of the Earth. We do this together. It's not because we want to send this message just now. Okay, so this message is start of a conversation, to encourage people thinking. And when we prepare this message, just before we submit this paper, there's a war between Russia and Ukraine come out. Okay, so people think, we forgot we are all on this together. Why we still have these wars? And so that brought my thinking about the ship stories. We are passengers on this ship. We don't know where we're going. Okay, we are looking at beacons. Okay, the only beacons we have, only beacons we know is us. We are beacons in the galaxies. If we send out this message, we are light up a beacon, say, hey, we are here. we want to find any others. Okay, maybe we can learn from something. If we find any others, we are going to learn how you survive in these cosmic oceans. And so from computer science point of view, and so the more I look at this message, the more I'm thinking maybe we need to change. Okay, for example, okay, all those, the RCB message is in lines. But if you read that code, there's no break of this line. How about if I receive this message, I just type, it's one line, then no picture is going to show up. If we redesign this message, we're going to have a page headings, page endings, and the starting of the line, ending of the line. We can do that by repeat something repeatedly. For example, B, okay, that's starting of the line. B, okay, that's the end of the line. You repeat that. When you read that message, you will see, oh, that's the start, or that's the end. If you line up carefully, then the picture is going to show up. Same thing is, we can design the headings and endings of each page. So that said, we carefully design this message, consult with computer expert, consult with the people's, and astrophysicists, biologists, and so this is our successful study. We work together over a year. We come up with these papers.